Well, this is what most of us imagine a robot would look like if we had one at home. It's an example of a programmable robotic system controlled by its own built-in microcomputer. It can move around, it can sense to some degree what's going on around it and act accordingly, and it can even speak.
Ready.
Ready. It's mainly used for educational purposes. In this series, we'll be looking at some of the principles behind using computers for control, what robots have been used for, and how to experiment with them at home if you have a microcomputer and are prepared to fiddle around with a lot of wires. Probably of all the use of computers, their use in control is going to have the most significant impact on the prosperity of a modern industrial society. Well, we first met Hero here, stripped to the waist as it were, at the world's largest robot exhibition in Chicago. Record crowds came to goggle at the latest weird devices to appear in this fast-growing international market. While industrialists were the main target for the hard sell, in America, there's a new consumer market for products like Hero.
Basically, we're seeing a lot of the electronic hobbyists buying them. The people that started with the first microcomputers are now taking it a step further and getting into the microcomputer-controlled robot.
But what can this robot do?
Hero has 5 senses. Hero can sense time. Hero has a motion detection system, which can sense a person walking within 15 feet of the unit. He also has a photo-optic system, which can measure 256 different levels of light. Hero has a sonar system, which can measure objects in its path up to 8 feet away with an accuracy of 0.4 of an inch. He also has a voice synthesis system, which can say virtually anything that's ever been said or ever will be said in any language. He can also measure 256 different levels of sound. What we're looking at now is one of Hero's 7 stepper motors, which is controlling the steering mechanism, which allows Hero to manipulate its way through environments in any given direction. It can rotate its wrist 350 degrees and open and close its gripper 6 inches with a closing grip force of 5 grams.
And how are sales going?
Very, very well. Very, very well.
Of course, most of the interest centered around the big clunkers, the powerful industrial robots. Unimation, the company which produced the first of them over a decade ago, is now part of the Westinghouse Corporation. This is how they use their own products to sell themselves.
Good afternoon. Not now. We have an audience out here. Can't you see all these people? Now, aren't you embarrassed? Sensitive artist. All right, I'm sorry I yelled at you. You forgive me? All right, I'm going to start the show now.
Unimation's first robots were installed about 20 years ago to do simple, unpleasant, repetitive jobs. Mechanically crude devices by modern standards, they lack the computer control which now makes robots so versatile. Today's machines are mainly used for jobs like welding or moving parts from one machine tool to another. This one's part of a machining center, which includes drills and grinding wheels. The part that's being moved from tool to tool is a plastic switch housing. In a sense, you can use the term robot for almost any programmable mechanical device. So this car transporter in a Swedish car factory can also be called a robot.
Hello, Coach Finch.
But as we'll see in later programs, computer-controlled devices are appearing in the most unlikely places. This one, called Uncle Clunk, is destined for the pizza parlors of the American South. And this one in California is likely to give any illegally parked motorist a nightmare. Where are robots going next? Joe Engelberger is said to be the father of the industrial robot.
Well, you can go beyond where we are and say, what are the more exciting things we're going to do? And I'll just mention a couple of them. One of them, we'll do by the end of this summer, neurosurgery with a robot. The computer will analyze the CAT scans. And out of that, we will tell the robot in tool coordinates where to place the drill over the cranium of the patient so that the hole can be drilled in and drip radioactive medicine. Now, the doctor stays with the scene, of course. The robot locks in the right position, then the doctor does the final operation. But we save maybe 5 or 6 hours of doctor's time. Another thing, and I'm building up to the household, is that we can take an arm, make it mobile, put it in voice communication, which is something we get out of the computer, and give an arm to a quadruple paraplegic. The arm will be spoken to in a high-level language, English or whatever. The robot will know the entire environment it's in, so that the patient can say, I'd like a sandwich, or make my guest a drink, or get me the book on the third shelf 4 in. All of those things will be known to the robot. Now, if I say we can do that, and we're experimenting at Stanford University with that right now, it's not a great extrapolation to say you can have a household robot.
Any of you fellas need a little shave or trim, just get in line here. All right, be neat now. Be neat. That's nice. Now comes the tricky part. They wanted me to sit in the chair, and I said, find yourself another dummy.
A slight bug in the program and you might end up with your head on the floor. You might say robotics is a cutthroat business. Well, most of the robots we've just seen were computer controlled. But before the computer became cheap, equipment in industry was what's known as hardwired. This is a beautiful model of a production line making gear wheels. It's got 3 machine tools, a drill, a router and a finishing tool, and robots to transport the gear wheels from one conveyor system to another. All the sequencing of events is controlled by the electronics in these boxes. Mostly they're switches, but they go on and off according to logical rules. The point is that if we want the machine to do something different, then we've physically got to reorganize all this spaghetti and rewire it in a different way. While we're in Chicago, we met Richard Fox, who was responsible for much of the development of robotics for Westinghouse. We suggested to him that the move from the first generation of robots that weren't controlled by computers to those that were had happened very quickly.
No, that's correct. In fact, the 2 robots that you see here are a good example of the great evolution that's occurred in robot technology and in control technology in the last few years. The robot in the back has no computer at all. It's all hardwired electronics on printed circuit cards. What that means is that the circuits are installed and are permanent, and the memory consists of wired core memories. 1s and 0s can be put in. The operator pushes the buttons to say, move this way, move that way. And then he pushes a button that says, record, and that stores the patterns in the 1s and 0s. When you look at the motion of that first robot, you see that it is very crude. It moves from taut point to taut point. Now, by comparison, the second robot is a computer-controlled robot. It has a 16-bit mini computer in its main memory, and it also has 5 8-bit microprocessors controlling the movement of each of the hydraulic motors in the robot control. The computer is used to control not only where the robot goes, but how it gets there. The motion is much smoother. You can accelerate, decelerate, even make sure that each of the different motors stops their motion at the same instant.
But this robot still isn't all that bright.
If you leave the part to be moved in the wrong place, the robot won't know it. And it'll reach over and pick up empty air and move it across and put down empty air. In the newest robot controls with multiple microprocessors, we're getting smarter. It now has some decision-making capability. If you know your basic language, an if-then statement or a go-to statement gets introduced into the robot programming lingo.
By analysing a picture taken by an overhead camera, this third generation or smart robot recognises which of a number of parts is present on a conveyor belt. It decides whether it's the right part, works out how to pick it up, and then how to move it to where it's needed, to assemble, in this case, an electrical relay switch. It's a task which a human could achieve quite easily. Yet this system uses very advanced software and relies on 6 linked 16-bit micros working flat out to control the assembly.
Computers are key in those systems, but what they're controlling can seem very complex, yet the principles are really quite straightforward. John Coll is with us today. John, what are you going to show us with this?
Mac, we've got a model computer-controlled conveyor belt. And like anything else, like any computer system, it's got devices which are input sensors here. And these input sensors detect the height of the object coming down the ramp. And there's another sensor here which determines whether the object's a metal object or a plastic object. Now those sensors are connected through to the computer system here. The computer system makes decisions and controls output actuators. For example, this device here pushes the object down the ramp. Now the computer program is set up so that it can sort out the objects, sort the large metal ones into one bin and the small plastic ones into another bin.
So by just changing the computer program, we can actually move which bin they're going to go into. For example, instead of that small one going to there, we could put it into bin number 1.
Yes, very simply indeed. If you look at the program listing here, you'll see that the lines here right at the beginning of the program control the destination of the objects. Line 130 says that the small metal object is to go into bin 4, where it went. And we can easily change that. Let's change that line, 130. Where do you want the small metal object to go?
Let's put it into 1.
OK. Well, in that case, we better take the large plastic object out of bin 1 and transfer it to bin 4. Right, and off we go. Now that large metal one goes through the metal sensor and down into bin 1.
Oh, that's beautiful. That's really neat. So that's completely controlled by the program here. Why is it moving so slowly?
Well, it's moving very slowly because the actuators themselves take quite a long time to move backwards and forwards.
It's not a limitation of the computer itself.
No, it's not. In fact, those actuators, you can see, are pushing the objects past those light beams and down the ramp, but the actuators have to move quite slowly.
What are those output devices there, or those beams there for?
Well, they're another sensor which actually sense whether or not the object has made it through down into the end bin, because the computer system might go wrong. Though the program's working correctly, the conveyor belt might go wrong for some reason. And if it did, you've got to have some method of feeding that information back into the computer program so that it can make a change decision, or it might have to switch the whole thing off.
So although it's looking as if it's working quite slowly, in fact the computer's doing quite a lot of work. Is it stretched at all?
Not really, Mac. It's got 4 sensors to sample, and the limiting factor really is the speed of the actuator, which is quite slow. So in fact we've been able to write the program to drive this system in BASIC. On the other hand, sometimes you come across computer systems where you've got to sample a large number of different devices and sample very rapidly. In fact, recently I went to see a very high-speed computer system operating a new car suspension system on sports cars.
So, Peter, what are the problems with normal suspension techniques?
Well, the purpose of a conventional sprung suspension is twofold. One is to absorb the bumps in the road in order not to transmit those bumps through to the passenger compartment of the vehicle, and 2, to keep the tyres in firm contact with the road for adequate stability and control of the vehicle. As a result, under braking, acceleration, cornering loads, the body of the car leans over, it moves around too much, and this hurts the handling of the vehicle. What we really need is a suspension that will do one thing one moment and another thing the next. It wants to be very soft for the bumps in the road and for ride, and yet it wants to be very stiff under cornering conditions so the car doesn't roll. This is basically fairly conventionally sprung. As you see, if we push up and down on the front of the car, it pitches and heaves and generally rolls a little bit.
Right.
Now, if you can change it, Steve. Now, if you push up and down in the same place, the car just moves vertically up and down. It doesn't pitch at all, and it doesn't roll.
Right.
A rather unnatural situation which you wouldn't necessarily use driving the car. Okay, Steve, switch off.
Right, so where's the computer then, Peter?
Under here.
Hidden under the bonnet, the computer's built to withstand very harsh operating conditions. All but one of these cards contains circuits that collect information from sensors on each wheel. The nearest has the digital computer and software to control the car's entire suspension system.
The human, of course, has the idealized suspension. It does this completely without the use of springs. It has a suspension which can adapt to downhill skiing, rock climbing, step climbing, walking, running, and it's basically muscles under the control of a brain, or a computer if you like. And what we've done is tried to simulate a natural suspension system. We have taken a hydraulic cylinder, and by measuring the load through this load cell here, which sends voltage proportional to load to the computer.
Right, so that's the actual cable that comes out of the load cell into the computer, right?
That's right.
Yep.
And this silver cylinder here measures the extension of the jack. And with suitable processing, the computer then sends signals back to this hydraulic valve here, which distributes pressurized oil to one or other side of the piston, and we are able to synthesize a spring.
Right, so it's an actual replacement, sensing what the car is doing and then responding to those positions and loads.
That's right, and in fact a little bit more than that is the engineer can decide under certain conditions that it should do one thing, under certain conditions it should do another.
So this black car, with its computer-controlled suspension, can be made to keep perfectly level under all driving conditions. Compare it with this car with a traditional suspension. And the driver can even change the way the car handles while it's moving, if he dares take his hands off the wheel.
Beautiful, but I suspect it'll be some time before we see suspension like that on your old family banger. It's really quite a complex feedback system, but using the computer as a switch is fundamental. John, I really like your old banger gear lever there.
Yes, this is Steve's idea of a miniature demonstration switch. We've got a computer system set up. This switch is connected to the computer and that controls the output. When I close the switch here, the light bulb goes off. When I open it, the light bulb goes on. Obviously, that's all the wrong way round, but that's because the computer program, which is running at the moment, continuously running. Now, let's see how the inputs get into the computer. The computer has a set of addresses, about 65,000 addresses in an 8-bit micro, and one of those addresses is connected to the outside world. And so by looking at one of those addresses, the computer can find out whether this switch is open or closed. If we move through the addresses rapidly, you'll see that this switch is connected to, I think it's 65,120 if I remember. Yes, that's the one. When I close the switch, this bit lights up, goes on, and when I open it, the bit goes off. But that's the input side of this address. Now, the computer is controlling an output bit under software control from the input bit, and it's been set up so that the output bit is always the opposite of the input bit. Now, that output there appears as a voltage across a couple of wires. In fact, these two wires here are the output from the computer system. That we would like to drive a light bulb. But unfortunately, a computer can't generally provide enough power to drive a light bulb directly. So we have to go through a piece of circuitry.
This is a kind of interface, really, isn't it?
That's
Between
exactly
the
what it's
computer and the
called.
bulb.
Yeah, an interface circuit. And we've actually got two interface circuits here. This first one takes the very small voltages and power coming out of the computer, amplifies it a bit, and makes this battery connect or not connect to the circuit onwards. Now, we could actually connect a light bulb across at that point there, and it would work it. But instead of driving a light bulb directly, we've gone one stage further, and we've said, OK, let's control a relay. And that relay is quite a big and powerful switch, and it's using this battery to control that bulb there. The advantage of using a relay is that you can control either a very large light bulb or a very large electric motor and so on. You don't really need both of those, but we've decided to show both.
Can we have a quick look at the program?
Yes, the program is really very simple. The nub of the program is this central bit here, and the central bit reads the state of the input, function input, into that variable switch state, and then it says, if the switch state is on, then turn the output off. otherwise turn it on. So that's really the nub of the program, and it just goes round repeating that section.
Because the real secret of using a computer as a switch is that we could, simply by changing the program, alter it. All we have to do is to alter that off to an on and on to an off, and it will put this back as it should have been. So when you switch it on, it goes on, and off when it goes off.
Yeah. You can alter it any way you like. If you look at this line here, I'll just change that line. And instead of saying proc output, we can say proc flash. Small change in the program, but look at the effect on the system. When the switch is open, the light flashes. When the switch is closed, the light goes off. So one small change in the software, one enormous change in the way the system operates.
And we haven't changed any wires. But this looks like an awful mess to have to wire one of these up just to have one light bulb at the end of it. And if you had lots and lots of these, it would be impossible, wouldn't it?
Yes, one of the major problems with interfacing is that you always have to get a soldering iron out and connect up loads of things. But it's very common that you require a relay to drive something else, drive a light bulb or something like that. So this box, called an interface box, plugs into the micro, into the computer, and it's got, in fact, 4 relay circuits inside the box, 4 relay outputs, and it's also got 4 switch inputs. And that box, quite cheap, replaces a whole load of wiring. Really useful, really cheap. Let me show you that in use on another application, which we've got over here.
Well, I recognise the noughts and crosses programme. Do you think Steve gets paid to make toys like this?
I hear rumours that he does, yes. What Steve's done is to take Ian Trackman's noughts and crosses programme and add some routines to it to drive this device. The routines, in fact, send signals out through the cable into the interface box, and from there the signals go on to drive the motors. But using the interface box means that he didn't have to build all the relay circuits that we saw before. Now, the device really just moves motors backwards and forwards and could be used as an XY plotter if you had a pen on it. Fairly simple device.
Well, in addition, it's got a little electromagnet there which enables it to pick up the pieces and then drop them in the appropriate point. So there's a switch controlling that. I suppose it's a sort of pick-and-place robot in the simplest terms.
Yes, but that's about all it is. It's got no feedback mechanism. For example, if there wasn't a piece there when it was trying to pick a piece up, it wouldn't know, and it would just go on playing quite dumbly. No intelligence, no feedback.
Well, this one looks a lot cleverer. It's rather a nice piece of work. It actually either plays itself at chess or it obviously can play you using a standard chess program.
It's got a whole load of pre-programmed strategies built into it which it can call on in developing the chess game. But we can see over there better how it works.
See if I can switch it
Start
on.
that one off as well. You can see that there's an electromagnet underneath the transparent piece of plastic which can sort of pick up the pieces and move them around. But I don't know on what chess basis. Oh, there, it took that piece. Right. Now, if we fool it, or if we muck it around, we can actually confuse it because it's got a sensor on the electromagnet which can be used to find out whether or not there's a piece there. And I'll tease it.
It knows
on
where
this
every
next
piece is, but it doesn't know which piece it's actually moving,
Yes,
does
it's
it?
not very bright. Now, watch this. It's going to come and pick that pawn up. There, now I've knocked it over and it's got very confused. Put it back and it collects it. And it's dropped it fairly near where it was meant to. But there's a sensor on that, so it can actually tell whether or not it successfully grabbed a piece.
Right, so it's a little bit more intelligent as a robot than that one. Thank you very much, John. Well, lots of people are keen to experiment with robots using their own micros, and strictly speaking, it isn't really necessary to be a software expert or even build your own hardware. One of the systems you can buy is this buggy, and it comes with its own software. At the moment, it's exploring this area and trying to map it out, and all that it's using to do that are these 2 front bumpers here, these switches. It can also have another couple of sensors here. There's a barcode detector at the front to detect lines on the surface, and there's a light source detector here. Well, next time we'll be taking a look at how other sensors can be used to give a much more realistic and accurate measurement of the environment. Till then, goodbye.